All right, let me try another video solution here. Here they say that you have a 70 kilogram ice hockey goalie. It's originally at rest. So I'll just kind of make this little scribble here for a goalie and give a 70 kilograms to it. But the important thing is to remember it's at rest. And the goalie then catches. Now that's a little misleading. Catches. I think a better word might be blocked. Maybe that's why a couple of you are asking me about this. Because catches a puck that has a mass of 0.15 kilograms. Slapped at him at a speed of 35 meters per second. Suppose that the goalie and the ice puck have an elastic collision and that the puck is reflected back. All right, so I'm glad they say that, because at first they made it sound like he catches it and it's in the goalie's glove, and the two are now connected together and there are one, and you can never have them stick together and still have an elastic collision. There would always be some heat created in that, and that's called an inelastic collision. But if it bounces off and ricochets, and that's what it says here later on, and the puck have an elastic collision, and the puck is reflected back in the direction from which it came, what would be the final velocities be in this case? So there's two of them. And so the first principle is conservation of momentum. And remember, momentum is conserved if you include all the parts that are interacting, which this is just be two. So if you include the puck and the goalie, you would have conservation of momentum. So before the collision, you would have the puck, which has a mass of 0.15, traveling at a speed of 35. So that's the linear momentum of the puck. And then plus the linear momentum of the goalie. So I'm including both objects. It's just kind of boring for the goalie because it's 0. And then afterwards, you would have, again, the mass of the puck times, I'll call it V1, the velocity of the puck after the collision. And then you would also have then the 70 kilograms of the goalie and then the speed of the goalie. But those two speeds are not the same if they aren't connected together. If they were connected together, I could say they're the same speeds. And that is, I think, now why people might be asking, because it says catches a, and it should be more blocks, and so it hits and blocks off, bounces off, maybe even hits the helmet of the goalie and bounces off, because it's got to be a significant bounce off to be elastic. Otherwise, there's some heat created, and most bounce off would be inelastic. Maybe it would hit a clothing or a leg or a skate or something like that, but you wouldn't have elastic. Anyways, let me do a quick calculation for this first one, 0.15 times 35. And so this is 5.25 equals 0.15 V1 and 70 V2. And maybe I'll just put a little box around it and say, all right, that is equation number 1. And because there are two unknowns, that is two different speeds, there's an infinite number of solutions that this can occur. Now, there's only one that would conserve kinetic energy, and so that's where the elastic comes in. We can say that the kinetic energy before the collision is equal to the kinetic energy after. Now, please don't confuse that with the phrase of initial energy is equal to final energy. That would also be true and always be true. But the kinetic energy is only conserved when you have something called elastic, and there's no heat created. In a I'll say normal in most circumstances, some of the initial kinetic energy as they interact and bounce off is turned into heat. And so the kinetic energy after the collision is not as much as it was before, and hence the name inelastic collision. But the energy would be equal on both sides because we would add up heat. So they give us something a little stronger than just conservation of energy. They give us conservation of kinetic energy. And there is no physical principle that says it has to be that way. It just says there are cases where that is true, and we call that elastic. All right, so if I were to look at the kinetic energy before the collision, it'd be 1/2, 0.15, and the speed before the collision is 35, and I'll square it. And the kinetic energy of the other object before the collision, the goalie, is 0. And so I'll work that number out in a second. But the other side of the equation would be 1/2 times 0.15 times V1 squared. And then 1/2 times 70 times V2 squared. So this is going to be the important piece that I need. This would give me a system of equations, 2 equations, 2 unknowns. So I'll go 0.5 times 0.15 times 35 squared, and this is 91.875 for the total energy and total kinetic energy before the collision. And it all remains as kinetic energy. And so maybe I'll just take half of 15. That would be 7.5. And half of 70 is 35. And maybe I'll put a little box around that. Okay, so using the physics principle of conservation of momentum and conservation of energy with the special case that it's elastic, I've got my 2 equations and 2 unknowns. And so there is only one unique equation for the intersection of these. Possibly 2. Because it's a parabola. But let's talk some more. Okay, so here is, like I said, my system of equations. Doesn't look like an easy way to solve this. Substitution is okay, but not very inviting. In other words, if I were to solve this for V1 up here and put it into here, then I would have this thing that would be squared. It would have a V2 in it, and I would have the V2 and then a V, and I would have a quadratic equation. And I suppose that's not the end of the world. It would, I guess, technically be just fine. But I'm wondering if I should take a different approach. No. Maybe I'll just stick to that original approach. Okay, so let me kind of keep working on this. Why don't I do, as I said, why don't I solve this one? So 5.25 minus 0.15 V1 equals 70 times V2. And if I divide it by the 70, and so maybe I should come down here. Okay, so I'm taking that, and I'm subtracting that speed, dividing by the mass of 70, and that's my V2. And I guess I'm going to end up squaring that and putting it into here. So let me do this. 91.875 equals 0.075 v1 squared plus 35 times this v2. And this would be 2.25 minus 0.15 v1 all over 70 and then squared. All right, so let me take the 91.875, 0.075 v1 squared. I'm trying to think if I separate this into two. I'll take the 70 and the square it with the 35 on top. So here's a 35 over, and 7 squared is 4,900. And then, remembering that a minus b quantity squared is a squared minus 2ab plus b squared. So this first term would be the 5.25 squared. So this is going to be a 27.5625. The middle term would be a minus, and it looks like it would be 2 times the first times the latter, 0.15, AB. And this would be 1.575 V1. And then finally, the B squared, 0.15 squared, would be 0.0225 V1 squared. All right, so 91875 equals, and I'm kind of wondering what I'm going to get here for V1 squared, because I have a V1 squared here, and I also have one here. That number, of course, would be multiplied by this outside. So let me go the 35 divided by 4,900. See, and that is really, really small. And so when I add it to the 0.075, I'm not sure it really changes it by much. It does add a little bit. I'll go 1607 V1 squared. All right, so I got something there. Let me go minus, and this looks like it too is going to be a pretty small number. It'll be the 1.575, then times the 35, then divided by 4,900. And this would be 0.01125 V1. And then this term, it's actually looking pathetically small also. 27.5625 multiplied by 35 divided by 4,900. And this is a plus 0.19, I'll call it 69. And like all of our quadratic equations, let's write it in standard form by moving this to the other side. So minus 91.875. And so this becomes a minus 91.6781. Okay, so if I go to solve this, maybe I should put page 1 here, page 2. Then I can say V1 equals, and it would be the opposite of B. So that would be a positive 0.01125 plus or minus the square root, and B squared would be 0.00125 squared minus 4 times A, which would be 0.0751607. Times a C, which is a negative number, so I'll put that negative out there and go 91.6781 all over 2A, which is 0.0751607. And remember, V1 is the ricocheting velocity. And so this is the negative number that I'm hoping to get. So I'll just look at the negative here. And so let me go ahead and take, well, I'll do this one first. 4 times 0.0751607 times 91.6781. That's like a 27. And see, when I add this number, 0.00125 square, it's kind of irrelevant, so small. Taking the square roots of all of that gives me a 5.25. Now, taking the negative 1, so I'll go times negative 1. So taking that and adding it to 0.01125. And then dividing that by a 2 and also dividing it by 0.0751607, I get a speed, not too big of a surprise, of a negative 34 point. And I was trying to carry a lot of extra decimals. I guess I should have justified that. It almost looks like I was careless with my significant figures, and I suppose I was, but I knew there'd be such a big difference between these numbers that most of the decimals probably could be done without, and so I'm going to go to 4 significant figures. That still might be a violation because they give 3 significant figures through all of them. But just to give a little bit of credit, I guess, to the fact that there's such a small change, this thing bounces off. And in fact, you could probably imagine that instead of hitting a goalie of 70 kilograms, it hit like a block wall that had millions of kilograms. Basically, the block wall wouldn't move. So in order to keep the energy the same, it must ricochet off and have the same magnitude, so it would have a negative 35 if it was a big solid object. That's why I was saying in my mind it's going to bounce off. That's why I was saying I knew it's going to be very, very close to 35. And that's why I felt like I needed to make sure I included a lot of extra decimals because of that small subtlety down here that I want to divide and have this big number, really that's negligible, and divide by that big number there, or that small number, so it comes out to be very close to 35. So I carried way too many significant figures to justify, and I'm even going to leave it at 4 to justify. In fact, maybe I'll switch over to the solution here. Yeah, see the author does a negative 34.9. And that's fine. That does say it lost a little bit. Okay. Oh, but it now allows me to go back to any of these other formulas and find velocity number 2. And maybe the place to go is all the way back to this one, which that one is actually the same as what we worked out right here. So velocity number 2 should be, and I'll just put this in, 5.25 minus 0.15 times this speed. Okay, and that speed is that number right there. So I'll go enter. And now that's the numerator. And divide that numerator by 70. And we're looking at a speed, and if I go 4 significant figures, it's 0.1500. 0.1500 meters per second. And it's a positive. So the goalie goes in the positive direction, which is the initial direction of the puck. Makes sense. Goalie moves back a little bit, but barely, because this goalie's a big object compared to the puck. And then the puck ricochets off, keeping most of its speed, again, because there's no heat. All right. But there's some good math there. And yeah, and that can be a bit of a challenging the math, let alone the two important pieces of the physics that we have, the principle of conservation of energy and the principle of conservation of momentum. All right, take care.